Okay, now our next speaker is Ekin Özman from Boğaziçi University. She is also a member of Feza Gürsey Center of Physics and Mathematics. And the title of her talk is Modularity, Rational Points, and Diophantine Equations. So let's hear Ekin. Thank you.
Thank you. Thank you very much for the introduction and invitation to speak. So I was also not sure about the audience, and I thought there would be lots of students. There might be lots of students, so I might have prepared a more elementary talk than it's supposed to be. If that's the case, I apologize from the experts to begin with. But let's see. So this, the main motivation of the talk will come from one of the main problems in number theory, which is, I think, finding solutions of Diophantine equations. And the one that we see on the first slide is one of the most famous of those equations, the Fermat equation. And it's a hard problem. It took hundreds of years for mathematicians to be able to come up with a solution to this Diophantine equation. But how do we approach hard problems if we have hard problems in math, especially if we don't have any idea of how to approach them? We try to associate the hard problems to an object that we know or that we maybe don't know too much, but we know it's important to understand, and maybe ask even a harder question to understand the first question. And in this case, that harder question is understanding the absolute Galois group of the rationals. I think it's might be fair to say that every number theory in one way or another, every number theorist in one way or another is trying to understand something about the structure of this group. So in our case, we will relate solutions of, we will relate the search of solutions of the Diophantine equation to understanding something about the structure of the absolute Galois group of rationals, which is the inverse image of the Galois groups of number fields, finite Galois extensions of Q. And how do we understand a group in general? One frequently used way is to look at its representations. So we are searching for representations of this group GQ that goes into the finite group of matrices, 2 by 2 matrices with coefficients in FB, invertible matrices. But where does this representation come from? This is the point where this totally arithmetic looking question relates to a bit of geometry because these representations do come from elliptic curves, which are geometric objects. And I just repeated the formal definition here, especially for students who might be in the audience. So here E will be an elliptic curve, and when I say E of K during the talk, all I mean is the set of solutions of this equation of the elliptic curve over the given field K in this case. In addition to these solutions, because since the equation that I wrote on the slide is an affine equation, we always solve this point at infinity as well. That's the meaning of K rational points of an elliptic curve. You can replace this K with any field of your choice, of course. And then we need also a notation for the p-torsion subgroup of complex points of E. So as all we know, points of an elliptic curve form an abelian group, and then it makes sense to talk about its p-torsion subgroup, meaning that the points on the curve, which gives you identity when you add them to each other p times. And because of the geometric structure of the elliptic curve, because it's a torus, the p-torsion subgroup is isomorphic to 2 copies of Z mod PZ. And that's where we get the Galois representation, because we know that these p-torsion subgroup is an algebraic group in the sense that the torsion points are defined over some extension of Q, some algebraic extension of Q. And therefore, we can talk about the Galois action on the p-torsion subgroup. The absolute Galois group acts on EP. And that gives us a multi-P Galois representation, rho EP, starting from the absolute Galois group GQ here, and goes into the automorphisms of the P torsion subgroup. And because of the group structure of EP, this automorphism group is isomorphic to GL2FP. That's where we get this representation. During the talk, I will most probably drop most of the time this E and P, if it's clear what kind of elliptic curve I'm talking about, but that's the full notation, okay? All right, so I just want to say one slide or so, a few words about the strategy of the proof of Fermat's theorem. This is just to motivate what I'm going to say next during this talk. And in fact, more of this strategy will be explained, I believe, by Yasemin, so tomorrow now, because her talk is rescheduled for tomorrow. And she will tell more about it, but I just want to say a few words just to motivate the rest of this talk. So that's the famous theorem of Wiles and Taylor-Wiles, that the equation of the Fermat equation has no non-zero integer solutions if the exponent is bigger than 2. What goes into proof is a lot of things, but there are three main theorems, three really important celebrated results that goes into the proof of this Fermat's last theorem. And the strategy is as follows. You start with a putative solution, and then you attach an elliptic curve to this putative solution. And then you try to show that this elliptic curve has very weird conflicting properties to each other, so that such an elliptic curve cannot exist, and therefore such a solution cannot exist. And that gives you the result. Of course, it's much harder than this, but I'm just trying to summarize it. So what goes into the proof are these theorems. The modularity theorem, I'm writing them in the reverse historical order. So modularity theorem is the last thing that has been proved. In fact, Fermat's last theorem is a corollary of this theorem. And then Ribet's level lowering theorem. And the oldest one is the irreducibility of Galois representations, the celebrated result of Mazur. I will say a few more things about these theorems, but as you recognize, I wrote the third one a little bit separately from the first two, because that's what I will be more interested in this talk. So this is the Galois representation that the theorem of Mazur is talking about, the one that we started this talk with. Okay. So what are these three theorems are saying? Very briefly, again, I'm not trying to write them in their full generality or nothing like that. I'm just trying to give the idea of these theorems. So modularity says that every elliptic curve over Q is associated to a modular form. More precisely, there is a modular function with this Fourier expansion, with the Fourier coefficients being an, such that the Fourier coefficients correspond to some special numbers, so-called A numbers, of an elliptic curve. What are these A numbers? They are defined as Q plus 1 minus the size of the solutions of your elliptic curve over the finite field of size Q. So the number of solutions of the Weierstrass equation of your elliptic curve over this finite field is subtracted from Q plus 1. That's the A number of your elliptic curve. So this right-hand side, as you see, totally depends on this elliptic curve. It's an integer. And the left-hand side is a Fourier coefficient, and the claim is that they correspond to each other. And then the Mazur's theorem, what does it say? It says briefly again that if there is an elliptic curve over rational numbers with full two torsion, meaning that all the two torsion points are defined over the rationals, then the corresponding Galois representation is irreducible for every prime bigger than or equal to 5. I will explain the meaning of being irreducible in the next slide. This is just now to remind or to explain very briefly what these theorems are saying. And the final tool that's used in the theorem is that it's an even more technical result than the previous two, but it says that under some special conditions, you can attach this elliptic curve that you have over rationals to not just the modular form that is described by the modularity theorem, to a more special modular form with a simpler, in some sense, with a simpler structure. This is proved by Ribet. And what's the meaning of this association? Right now, you don't have an equality between the A numbers of your elliptic curve and the Fourier coefficient of the modular form, but you have a congruence, so it's a weaker association. However, the corresponding function, the more corresponding form, is simpler than the one that modularity theorem gives you. Okay, so those are the three main ingredients, and then how they come together, at least in the case of Feynman's last theorem. Just let me repeat this part. Yasemin tomorrow will give you even better examples of how this machinery works. Right now, we have a lot more complicated equations than the classical Feynman equation that we can solve using a modular approach, and that I believe will be explained tomorrow by Yasemin. But the simplest case can be summarized as follows. So we have a putative solution given by ABC to the Feynman equation, x to the n plus y to the n is equal to z to the n, or p, let's say the exponent is p, doesn't matter. Then we construct this Frey curve associated to this solution. And this Frey curve has a very special properties. Its minimal discriminant, as you see, has a very special form. This is very important because all the missing ingredients, in some sense, you don't know what the elliptic curve is because you don't know what the solution is. You don't know even if it exists or not. But all this mysterious ABC goes together, packaged together with the exponent p, and the rest is just some constant. This is the form of discriminant that we require, that we look for every elliptic curve that we attach to putative solutions of Diophantine equations. That's the key point of having a Frey curve. Anyway, so we have this Frey curve, and then we look at its representation, Galois representation. And we can apply Mazur's theorem and conclude that this representation is irreducible. And then we can apply also the big result of Wiles and conclude that E is modular. And together with these two, we can apply Ribet's theorem and say that this Frey curve is associated to a new form of level 2. Okay, but then what's happening? Computing new forms of a given level is not so big of a deal, in the sense that operations, for example, many computer algebra programs can do this for you. They're explicit algorithms. And in the case of level 2, we see that there is no such new form. So if there is no such new form, this means there cannot be such an E. That means there cannot be such a solution ABC. So that's how you get the result as a corollary to modularity theorem. Okay, so one of the key ingredients here is Mazur's result, which says that for big enough primes, this Galois representation is irreducible. In more precise words, it's not upper triangular. Okay, so let's try to understand the meaning of this a little bit more. So we are looking for Galois representations such that they become irreducible for big enough P. But how can we study these? Like you want to study an infinite family of these. And how can you do this? You need a parameterization. You need another object that packages all these representations into itself. And that is done, that can be done by an algebraic curve, so-called the classical modular curve, denoted by x0p. And the parameterization is as follows. The points on this curve x0p are in correspondence with irreducible Galois representations, with representations that are given by these upper triangular matrices. So in some sense, if you can say that this classical modular curve has no rational points, or to be more precise, it has no rational points other than cusps, then the representations that you're looking for are all irreducible. So I'm going to say a few more here, like the X0P. What is X0P for somebody who's not familiar with it? It's an algebraic curve, meaning that it has a Diophantine equation that is defined over rationals, or even integers if you want. So, and you are trying to ask yourself when this algebraic curve has rational points, for instance, or in other words, when does this Diophantine equation has solutions over rationals? Again, I'm not talking about, I'm disregarding cusps. Cusps are always there. Cusps are not my concern. Okay. So what did we do? Well, we started with the Diophantine equation, the classical Fermat equation. We were trying to solve it, and somehow we found ourselves in this world of Galois representations, which is parameterized by this modular curve X0P, which is another Diophantine equation. So we're trying to solve one Diophantine equation, or an infinitely many family of Diophantine equations, with another infinite family of Diophantine equations. It looks like we are back to square one, but it's not the case, like, because we have, this was proved before. We have Mazur's big theorem, so that this was ready for us when time came finally for Wiles to prove Fermat's last theorem. This is just, again, to illustrate what's the meaning of an classical modular curve. This is an affine model for one of the modular curves of level 43. And I'm trying to understand solutions of this f of xy over rationals, for example. Okay, this is just for one particular level, and what Mazur did is understanding this set for infinitely many levels. So that's why it's such a big result. Mazur proved that if n is bigger than 163 and prime, then the corresponding modular curve has no rational points other than the cusps. Again, cusps are not surprising. Cusps are always rational points. We know what they are, so that's not big of a deal. But other than those cusps, there are no rational points, no matter what the level is, if it's big enough. Okay. Later on, this result has been generalized to composite levels as well, and smaller levels have also been studied by Kenko and Momose. So we have the full result. Okay. All right, so that is the the very brief summary of classical Fermat result, and how Mazur's theorem is used during the proof of this result. What would you do if you are trying to solve other Diophantine equations via the similar methods? If you want to run the modular approach to other Diophantine equations, how can you do that? What is needed? So when I say other Diophantine equations, I mean like equations of this form. You can change the exponents. They don't need to be all the same integer, PQR in this case. Or you can maybe keep the exponents as they were before, but add some coefficients. So this is sometimes called generalized Fermat equation. Or you can do both. You can change both the exponents and add coefficients. So these are all similar type of equations, and we expect to have similar type of proofs to work in these cases. That's one question. Or another thing you can ask, why not study classical Fermat equation over other number fields, not necessarily Q, but over higher degree number fields? This is also not a new question. Many work has been done in this area. What is needed? Well, what is needed are the generalizations of what has been used in the classical proof. So we need the modularity of elliptic curves defined over larger fields other than the rationals. We need Ribes theorem over larger fields, some sort of modularity, some sort of Ribes theorem, and we need Mazur's theorem over larger fields. So it's not an easy task to do. And again, in this talk, I will concentrate on this red part. What can we say about Mazur's theorem over larger number of fields? What can be said about the Fermat equation over larger number of fields, or what can be said about generalized Fermat equation over larger number of fields, is Yasemin's job for tomorrow. Anyway, okay. So I think it's fair to say that to solve Fermat type equations over higher degree number of fields, K, we need to understand the K rational points on the classical modular curve, X0n. This is one motivation, but in fact, it's not the only motivation, or it's not really fair to restrict this question to the motivation of solving Fermat type equations, because this question itself is also extremely important, I believe. Let me just compare this with X1n. X1n is also another very well-known modular curve. Its points, the K rational points of X1n, parameterized, elliptic curves defined over the field K with n torsion rational points defined over K. So unlike X0n, this parameterizes elliptic curves with a point. X0n, as we have discussed before, parameterizes reducible Galois representations, or in the language of elliptic curves and torsion groups, it parameterizes an elliptic curve and a subgroup C, which is isomorphic to Z mod nz. That's one way of saying it. Or it parameterizes elliptic curves E with n-cyclic isogeny. Okay. And this is what they do, but the results that we know about these K rational points are quite different. So for X1n, we know a lot of things. By Mazur's work, we know that X1n consists of cusps if the genus of this curve is bigger than 1. Then we have the famous result of Merrill that says that if you have a number field of degree less than or equal to D, then there is a bound that only depends on this degree D, doesn't depend on the number field at all, just depends on the D, such that if the level is bigger than this bound, the corresponding X1n consists of only cusps. Okay? So we know a lot of things for X1n, about the rational points of X1n defined over higher degree number fields. We even have more precise result by many other mathematicians. However, if you ask the same questions for X0n, the case is less happy. We don't know much. Here's what we know so far. So I will concentrate on quadratic points. There are some results about cubic or quartic, but they are not too clean to state. And you will get the idea what I mean when I say that. So what's a quadratic point? A quadratic point is a point whose field of definition is of degree 2. So when I say QP, I mean the number field that I obtain by adjoining coordinates of this point P into Q. Okay, so I want this extension to have degree 2. And here are the things that we know about quadratic points on X0n. So if the genus of your curve is at least 2, then it has finitely many quadratic points, except for 28 values of n. That's a result of Bars and Harris-Silverman. Then we have the result of Braun and Najman. They parameterized all quadratic points on X0n under the following restrictions. They want the Jacobian of the curve to have modular rank 0. And they want the modular curve to be hyperelliptic. So when you put these restrictions, the corresponding values of n are the ones that are in the set. So for these values of n, they found and parameterized all quadratic points. I just want to emphasize here, like, this is a finite list of n. So we're talking about a finite list of curves. But when I say quadratic points, I mean the points that are defined over any quadratic field. So the list of fields are infinite. Even though the degree is fixed, the fields are infinite. Okay, sorry. So after those, we had proved together with Samir Siksak a result about quadratic points on x0n under the constraints that, again, the Jacobian has 0 modular rank, and the genera of the curves are in between 3 and 5. So this gives, again, another finite list of n. Under these conditions, we found all quadratic points. And in this case, and at this stage, we have a full list of all possible quadratic points on these curves, with genera being 2, 3, 4, or 5, under the restriction that the Jacobian is torsion. Okay, after this, we have another result, which is quite related. Box got rid of the condition of torsion Jacobian, and for the same genera, 2, 3, 4, 5, all quadratic points have been determined if the Jacobian has positive rank. So that is another handful of n. So let me summarize what we have. We have a full list of all quadratic points on x0n if the genus is between 2 and 5. Okay. And you might ask, all right, this is something, but why is it helpful? I think it's interesting of its own sense, but an actual application of this is
can you go to the previous slide, one before this?
Sure. Yeah, this one.
Yes. So, can I ask a question? I mean, sorry for interrupting. So if the modular rank is 0, so it's torsion.
Yes.
Then you give a finite list of n for the fixed genus for the genus between 3 and 5.
Yes.
And if the rank is positive, the n is also finite number of n's, right?
Because the genus is also 2, 3, 4, or 5.
Oh, okay.
In this case, yeah. So there's always a restriction. It's always a finite list of curves that you are talking about. So basically, Box completed the missing curves in this genera.
Okay, thank you.
You're welcome. All right. So before I say why this is helpful, I just wanted to list all the 3 results. So you see that I forgot how many, but it's not so many elliptic, not so many modular curves, but still helpful. And why it's helpful? Because you remember, we need the irreducibility of the mod P representation of a Frey elliptic curve, E over K. And this Frey elliptic curve often has extra level structure in the form of a K rational 2 or 3 isogeny. So if the mod P representation is reducible, which you don't want, you want the irreducibility. But if the mod P representation is reducible, combining this with the K rational 2 or 3 isogeny, you should obtain a point on x02p or x03p. So understanding the K rational points on these modular curves of small level is helpful in the case of solving the Fermat type equations, or even the classical Fermat equation, over quadratic number fields. And this has been, for example, applied by Freitas and Siksak to study quadratic solutions of the classical Fermat equation. What is used in this case, in this paper, they needed the full structure of the quadratic points of X034. So this is something that is covered by our results with Samir Siksek. And I just want to show you what kind of, what do we mean by parameterization or list. This is what we mean. So this is a model for this classical modular curve of level 34. And these are the points that we find, all the quadratic points, there is nothing else. This is their field of definition. So the first three are defined over Q adjoin square root of -1. We have another one defined over Q adjoin square root of -2, and two more defined over Q adjoin square root of -15. Okay, and we find their coordinates with respect to this model, the J invariant of the elliptic curve corresponding to this point, whether or not this elliptic curve has CM, so on and so forth. Just one thing that's not very important maybe, but the points that we list here are not, so if we have P4 here, of course, the Galois conjugate of P4 is also a point on this curve, but we don't list it because it's obviously there. Right? So as you see, only over 3 different degree 2 number fields, this curve has a point. Right? That's very few. All right, so maybe I should say a few words about the idea of the proof, because it's a computational result, and sometimes it's hard to explain why computational results are not so easy, or what goes into the proof, but let me try it anyway. So first of all, the theoretical approach. How do you approach such a question? If you have a curve, how do you try to find its all quadratic points on it? So in our case, we have a non-hyperelliptic curve. We know its Jacobian is finite. And we also know that there is a rational point on our curve, which is a cusp, for example. Okay. That's one thing that you need to run this theoretical approach. The second thing you need is that, let's say, since you have a torsion Jacobian, let's say you can enumerate all the points on the Jacobian, which is not something easy, but let's say you can do. Then you form the symmetric product of this curve, and a rational point on the symmetric product implies 2 things. So a rational point on the symmetric product is a set of 2 points, P1, P2. Either these 2 points are themselves rational over the curve, or these 2 points are defined over a quadratic extension, and they are Galois conjugate of each other. Okay? So if you want to understand the quadratic points of your curve, you are in fact trying to understand the rational points on the symmetric product. So how can we understand this set now? We construct a divisor given by P1 plus P2 associated to this point P on the symmetric product, and then consider the natural embedding from the symmetric product into the Jacobian, given by this, sending the point P into this class given by dP minus 2 times P0. P0 is this given rational point on your curve. Okay. And the idea is, since you can, if you can enumerate the rational points here, by pulling back these finitely many points, you can possibly determine the rational points on this symmetric product. That's the idea. Okay, but again, it's not easy to do this. So let's see why. So I have this point in the symmetric product, the corresponding divisor. It is associated to d prime plus 2 times P0 for some divisor d prime on this Jacobian. Degree 0 divisor on X is d prime. For each d prime, we enumerate effective degree 2 divisors that are linearly equivalent to d prime plus 2 times P0. And then we compute the Riemann-Roch space of this degree 2 divisor. Since you are dealing with a non-hyperelliptic curve, you have 2 choices here. Either this Riemann-Roch space has degree 0, which means there are no effective degree 2 divisors D that are linearly equivalent to this sum, or it has dimension 1, and you find F, which is not 0, in this Riemann-Roch space. And then you get the unique degree to divisor that you are looking for by using this F. However, this theoretical approach most of the time doesn't work, because there are several problems. One of them is everything relies on enumerating this rational points on the Jacobian, which is something extremely hard most of the time. Not even like, it's not possible to do this computationally. Even if you can do that, then you're doing lots of Riemann-Roch computations, and anyone who has dealt with this knows that making a computer do these kind of computations is not easy. I mean, if you're lucky, it might work in a few cases, but you very quickly run into problems as you increase your n, for example, or as soon as you come across the Jacobians, which are not so small. Okay. All right, so what did we do instead? So instead of trying to compute everything, the full Jacobian, we decided to work with a rational subgroup of this Jacobian, which is very easy to compute, which is very well known, which is like right there. You can even write it by your hand. It's the rational cuspidal subgroup. And we know that by Manin-Dirichlet theorem that this rational cuspidal subgroup is a subgroup of the torsion subgroup of the Jacobian. In our case, everything is torsion, so we're good to go. And by rational cuspidal subgroup, I mean the subgroup of divisors that are generated by cusps, and that is a rational subgroup. So there's an important conjecture here, generalized Ox conjecture, which says that this subgroup relation is in fact an equality. So in fact, by approaching the problem via this C, we are not losing too much, because conjecturally they are the same. And in fact, if in most of the cases we were able to show that they are the same, so we had even more proof for Ox conjecture. Okay. So that's the first step. Write down the rational cuspidal subgroup. It's immediate. And then bound the index of the subgroup in the Jacobian. Let's say that's bounded by I. So I times the group that you're looking for is inside C. And then the effective degree two divisors that we seek satisfy an equality. This I is this bound. Okay. And then that's not, so this is already a simplification, but that's not everything. Then we apply a version of Mordovaya sieve. Maybe at the end of the talk, I will have some time to tell you a bit about the Mordovaya sieve, but this is just another way of eliminating even more divisors. So at the end of the day, there are only a handful D prime left that you have to compute the Riemann-Roch space of. So that simplifies the computations a lot and lets you to compute what you need actually. Okay. So after all these, what is the result? For these values of n, we were able to show that there are no quadratic points if D is not one of these. Okay, so only quadratic points that are defined are for these fields. So maybe then one can ask a question whether this is always the case. Can we find a bound B such that for all D whose absolute value is bigger than this bound, the corresponding modular curve doesn't have any quadratic points for any level? That's a widely open question, in fact. Okay, so I guess I have like, how many, 30 minutes left or so, I guess, if I'm not mistaken. Okay, so that is exactly the half of my first part. So one motivation of studying K rational points for the classical modular curve, for me at least, came from proving Fermat type results over higher degree number fields. But
Ekin, you have 20 minutes, by the way.
Okay, thank you. Thank you. Thanks for the
So
correction.
before you move on, can I ask a very elementary question?
Go ahead, please. Yeah, sure.
Okay, so these quadratic extensions, do you
Yes.
know the class numbers of these?
I mean, they are not all one, of course, I can say. There is no, I mean, of course, I know what the class numbers are, not off the top of my head, but there is no pattern. They can be even, they can be odd, if you're asking about that.
So, but you know the class numbers of all of them?
There are even ones as well.
Okay.
Yeah, there are even ones, there are odd ones, so there's not like a full pattern, I can say.
Thank you.
Okay, so Mazur's result was just one of the things that is needed for modular approach. Another big piece is the modularity theorem, of course. Then that's even more mysterious. We all know that we are so far away from getting modularity over arbitrary number fields. We have a few satisfactory theorems, though, in a few cases. For example, we know that elliptic curves over real quadratic fields are modular. This is a result by Freitas, Lehang, and Zigzag. We know that elliptic curves over total real cubic fields are modular by Derrick, Snijman, and Zigzag. And we also know the following, that the Q curves are modular by Kara and Wintenberger. So what's a Q curve? A Q curve is a special type of elliptic curve, not so special though, but so it's an elliptic curve defined over a number field, K, let's say, which is isogenous to all of its Galois conjugates. So the curve itself may not be defined over K, over Q. It may not be rational. But up to isogeny, it is rational. The isogeny class is fixed. And if this K is quadratic, we say that E is a quadratic Q curve. Okay. And what we know about Q curves are that they are modular. So it's a big class of elliptic curves, and we know they are modular. Okay, so using this fact, we can do the following. So this was the idea for the classical Fermat equation. We can adapt it for another Diophantine equation, for example, the following one, a to the 4 plus b squared is equal to c to the p. Exactly like in the classical Fermat case, we associate a Frey curve to this. And this time, this is a curve, as you see, not defined over Q. We have I's here. So it's an elliptic curve defined over the field Q adjoin I. And it's a Q curve. Okay? It's isogenous to its only Galois conjugate. And this Q curve has unusual properties, exactly like in the case of the classical Frey curve. This is a result by Ellenberg and Skinner. I'm not gonna say what kind of unusual properties. It's not necessary for us right now, and it's a bit technical. But we can run the modular approach for this equation, given this result of Ellenberg and Skinner, and obtain the following, that the corresponding Diophantine equation has no solutions for p greater than 211. So this is just an example of like why Q curves are of help in these type of questions. We don't know the full modularity, but we know something is modular. So why not use that something to get information about some type of Diophantine equations. But to do that, we need, again, to understand the structure of Q curves. We need to parameterize Q curves. Okay, how can we do that? Well, let's recall that the classical modular curve is a moduli space of elliptic curves with associated cyclic subgroups of size n. And the moduli space that parameterizes quadratic Q curves is a close relative of this classical modular curve. It's a twist of this classical modular curve. So I'm going to explain this red sentence. It's a twist by Wn in a second. But in general, what's the meaning of a twist for a general curve? it's something very easy to describe. A twist is another curve defined over the same field. So if your original curve is defined over Q, its twist is another curve over Q again. And the twist is isomorphic to the original curve over the algebraic closure of Q. So these two curves, X and its twist, are geometrically the same curve. Over the algebraic closure, they don't differ at all. But arithmetically, they are quite different. Over Q, they are not the same curve, because the action of Galois is different on these two curves. And you can parameterize the twists, you can understand the twists of a given algebraic curve X via studying the cocycles, special cocycles. So the twists are in one-to-one correspondence with this cohomology group. Right. Okay, now I want to describe this specific twist that I'm trying to explain. So this definition has a Wn on it. And what is Wn? It's an involution on this classical modular curve. What does it do? It takes this tuple E and the isogeny phi. Phi is an isogeny of kernel isomorphic to Z mod and Z. And Wn just switches this E and E prime and replaces phi with its dual isogeny. Every isogeny comes with a dual. Okay? So that's an involution. That's an order 2 automorphism of X0n. And now we will define a cocycle, and that cocycle is going to give us a twist. And the definition of the cocycle is as follows. Given this quadratic field with the non-trivial Galois element being tau, this cocycle takes this tau and sends it to Wn. And therefore, the definition of tau on X0n is twisted in some sense. It becomes, so when I show this new action as a power, and the definition now becomes Wn composed with tau. Okay? And now the twist corresponding to this cocycle will be denoted by X0d. And the rational points of this twisted curve are k-rational points of the classical curve that are fixed by this composition, Wn composed with tau. It doesn't matter which order you pick. Okay. All right, so again, what do we know about these two curves? We have X0n and its twist. These are isomorphic over the quadratic field K. They are not the same curve over Q, obviously. X0, this twist is also a moduli space. Its rational points parameterize the quadratic Q curves that we are interested in. So if you can understand the rational points of this curve, you will have information about Q curves, which might be helpful for you for your study of Fermat-type equations. Okay. All right, so this is what I repeat about the moduli space structure of the twisted curve. So what's the natural question now? Do we have a point there? Does this twisted curve has a Q rational point? If yes, for which D and N? If no, for which D and N? And the quick answer is not for all D and N. And just one little remark here, the twisted curve, this set might be empty. The twisted curve may lack any rational points, unlike the classical curve, because the classical modular curve have cusps in it, but the cusps are rational and they are interchanged by Wn, the involution. So they cannot be rational points of the twisted curve. So this set may well be empty. Okay. Another remark is that the rational points on this twisted curve are a natural subset, obviously, of this classical modular curve over the quadratic number field. And therefore, here comes it again. Knowing something about the k rational points of X0n may also be used for this problem. Okay? But this is a smaller subset. This is a more refined question. In fact, understanding this is even more applicable in some cases. Okay?
Ekin Hadi has a question, I think.
Oh, sorry. Sure. Go ahead. I don't see.
You say that if E is a Q curve, quadratic Q curve of degree n,
yeah,
then this gives you a point on X dot D, right?
Yeah, exactly.
So, don't you need to fix an isogeny? also on E?
No, because so this is you don't need so this E pure means that it's isogenous to its Galois conjugate. It doesn't matter like it can have more other isogenies as well.
No,
But
I'm saying that X naught itself wasn't it didn't it parameterize elliptic curves together with some points?
exactly, it's some isogeny. No, X0n.
Yes.
Yeah, and so maybe like let's go back to here. So the points on X0n are points of this form. They are fixed by this composition, tau and Wn, right? And Wn replaces these 2 points, E and E prime. And tau is this Galois conjugate. So what I have here is that E, and then phi between E and E tau, for example, that is fixed by this composition. So that gives you an isogeny between E and E tau. And that gives you, you're welcome. Okay, all right, so I was here. Okay, so what's the first thing you try to answer if you are trying to find global points of an algebraic curve? Well, the first thing to ask is, are there local points? Because if there are no local points, then there are no global points. That is described, summarized by Hasse principle. I believe all of us are familiar with this, so I'm not going to spend too much time on that. So first question, given NDP, what can be said about the local points on this twisted curve? Something that can be said is the following. There are explicit and very easy to check conditions that tells you whether or not this local set is empty or non-empty. So we have the necessary conditions, at least, to have local points everywhere. That may not be enough for global points, obviously. But then you can ask the following. Among those twists that has local points everywhere, how many of them are failing to have global points? Can you tell asymptotically how many there are that are violating the Hasse principle? And again, the answer is yes. It's possible to give such an asymptotic. And in fact, they have positive density. Just to illustrate this result, I wanted to give an example under the following restrictions. Let's say we have a prime n, which is 1 mod 4, a positive integer z, and we are looking at the set A, the set of positive square free integers, d up to z, such that the quadratic twist by this field defined by d and Wn violates the Hasse principle. So A is the set of twists that has local points everywhere, but no global points. And this set A has size asymptotically given by this fraction here. And this constant C is just a constant that depends on n, so is alpha. Okay. All right, so like we have conditions on the existence of local points. We have a result that says that many are failing to have global points. And then a natural question is why that's the case. What are the reasons of these type of violations? And can it be explained by Brouwer obstruction, or in this case, it's equivalent to say, can it be explained by model-based sieve? So this is the point where I might try to summarize model-based sieve. The idea is very nice, I think. That's why I want to summarize it. So here's the idea. It works for any curve. Let's say you have a curve, you are looking for its rational points, and you know the existence of one rational point, P. You send it into its Jacobian via this natural embedding, and then you also look at the reductions on both sides, reductions mod P. Where this P is belonging to a set of finite primes. So this S is a set of finite primes. And so you have these reductions on the left and right and injection on the top and bottom. And this is the commutative diagram. So if you start with a P in this XQ and then follow these arrows and come to this corner on the rightmost down here. And if you do the same thing or via the other path, then they must intersect, okay? If there's a P here, I can follow these two arrows and reach here, or I can follow these two arrows and reach here, and these two images must intersect. If they don't, then there is no such a point to begin with. Okay, then the XQ is empty. That's the idea of modularity. Why it's helpful? Because obviously computing these points here, since this is over a finite field, is more approachable. Okay, so typically this is what we do. When you have a curve of genus at least 2, that's what we do. We use this to explain Hasse principle violations. How much time do I have? Am I over time or?
Let me check. You have 4 more minutes.
4 more minutes. Okay, good. Okay, so if my last thing to say is that this usually works for genus 2 curves or higher genera curves, but for genus 1, something else happens, and that something else gives you another question. Which makes sense not for modular curves, because I mean genus 1 x0 and they are only a few. That's maybe not so interesting, but if you just say elliptic curves, it's a lot more interesting. It's a bigger family. So for genus 1 curves, this question about twists translates into the following. It translates into a trace question. Maybe I will just show you the full slide and then talk. Yeah, that's easier. So if you look at the third item here, the rational points on the twisted curve are k rational points that are fixed by tau composition Wn. And in the case of genus 1, Wn is just the following map. It takes a point, negates it. Negation is meaningful because I have an elliptic curve, and translates it. So this Wn is not an elliptic curve automorphism. It's an automorphism as a genus 1 curve because there's a translation here. Okay? So that's what it does. Takes a point, negates it, and translates it. And I'm trying to figure out what kind of points are fixed in this sense. Okay. So if you translate this, you're asking the following: my twist has rational points if and only if the image of the trace map 1 plus tau can be taught as a trace from the quadratic field to rationals. My twisted curve has rational points if and only if the image of the trace is containing the point S. Okay, S is not an arbitrary point; it's this S here that determines my Wn. Okay, so that same thing holds for local points as well. So if you translate the Hasse principle, local global exchange, into trace, you get the following question: do we have any local global trace obstructions? Okay. So here's the precise question. Let's say you have an elliptic curve. Forget about modular curves. You don't have to know anything about them now. If you have an elliptic curve, fix a point, a rational point on this elliptic curve. Let's say this point is a local trace for every prime. Is it also a global trace? And that's something that we worked on together with Mirella Ciperiani. And we got the following results. I'm not going to read it, but basically it says that it gives you conditions when you have local global trace abstractions. There are 2 different results. You have to study the 2 torsion points separately, but it's a complete result at the end of the day. Okay. So we give an answer to this question. This is just a summary. So check how do you answer this question. Check if there's a trace obstruction for 2 torsion points. If there's no trace obstruction for 2 torsion points, then you can check for the rest. Okay, that's just maybe a very quick summary. Anyway, so I'm finishing now. Just to wrap up, where did we start the journey? We were trying to understand solutions of a Fermat type equation. It was a very simple equation you can even ask to a high school or elementary school student maybe. And then it led us to questions about modular curves, about points on modular curves over higher degree number fields. It gave us questions about modularity in general, or modularity of special class of elliptic curves, so-called Q curves. Then that question led us to study of violations of Hasse principle and reasons of those violations. And then if you study those questions for genus 1, you get the trace obstruction question. So one little problem gives you tremendously many other interesting problems. And that's number theory. And I love to end my talks with this quote from Mazur. I'm sorry for people who have seen it before. It's my old joke, but that's what I like. So you can read it. But that basically says that don't get fooled by easy questions of number theory that may cost your life. I'm done.
Thank you very much. So, any questions or comments? Yes, it's fine.
Actually, thank you for your very beautiful talk. So my question gonna be again absolutely silly one. So the question is that what are the obstructions for, like, I mean, treating higher degree extensions? So one thing that I have realized is like related to the symmetry of the Hecke. Yeah, you have, I mean, made use of this sort of two symmetries, so this sort of mirror symmetries. But I don't know, maybe one can formulate things like, I mean, some sort of symmetries inside, like iterated Hecke or something like that, that can help to
So when you say obstructions, you mean obstructions to understanding k-rational points on x0n?
Yeah, for higher degree extensions. So let's take like cubic.
What I would do first was go and check what Mazur did for x0 and q, right? And there he works with quotients of j0n with small enough quotients, but also they are big enough to give him some independence, linear independence of Hecke operators, as you say. But that thing fails when you extend your extension from Q to K. In other words, that method of Mazur fails because the Jacobian has quotients of positive rank, which ties your hands. In the case of Merel for x1n, what he did, he kind of mimicked Mazur's proof, but he were able to find a optimal size quotient of J1n, so-called the Winding quotient. That the analog of Winding quotient for J0n does not exist. That's what makes generalizations of Mazur beyond, like, I mean, we don't have, the same technique doesn't work, that's for sure. We have to invent something else.
Okay, thank you very much. So I think I roughly got the idea. I roughly got the point. Thank you very much.
Any more questions or comments?
I want to say thank you very much. This was a very beautiful talk.
So maybe I will make one small comment. Actually, among the audience, there is Ali Rajai. He is a former student of Andrew Wiles.
Oh.
And actually, he was doing his PhD when Wiles just announced his big proof of Shimura Taniyama. And there was, of course, this small error, and he fixed it with the help of his former student, Richard Taylor. And during those times, Ali was a student at Princeton. So maybe during the conference, from first hand, we can hear some
witness of the history.
Yeah, thank you very much. So I will stop recording here now, if there is not any more questions. Okay.